All right, so the last thing in this unit is projectile motion. Projectile motion is going to incorporate everything we've done in this unit except graphing. All right, so there's going to be some v equals d over t calculations. There's going to be some acceleration calculations, and there's going to be some vector related stuff as well. All right, so a little bit of everything in this part of the unit. There's two types of projectile motion. Okay, there's a projectile that's projected horizontally, and then there's a projectile that's projected at an angle. Right? Anytime you throw something, what eventually happens to it?
Comes down.
Yeah, it comes back down. Okay, maybe not. I mean, if you throw it straight up in the air, it comes straight back down to you. Okay, but if you throw it horizontally, it still eventually hits the ground. Everyone okay with that? Okay, if I throw it in an angle, let's say I throw it equally hard. I throw one, like just two balls. Okay, I throw one ball horizontally as hard as I can. It hits the ground. If I throw another ball, it's identical, and I throw it just as hard, but I throw it at an angle. Which one will go further? The angled one. All right. And the reason for that is what? It's higher off the ground. Okay, and because the one I throw horizontally isn't moving vertically when I let it go. The one I throw at an angle is moving slightly upwards. So it takes gravity longer to pull it back down. That sort of makes sense? All right, so what we have to remember here is that gravity is always acting, okay, on any projectile. Now, to simplify things, we're going to eliminate that air resistance is also always acting on any projectile, because air resistance can really be inconsistent. Okay, it can depend on all kinds of things like wind direction, air density, relative humidity. Okay, all kinds of things. So even through a short path of a projectile, the air resistance can change on it during even a short path. So we're going to neglect air resistance because it's just too much of a bother to kind of track it. Okay, so that leads to some of the things that we see with real world projectiles. Okay, if I have this situation, let's imagine this. I have two bullets. Okay, one is just sitting there. The other is in a gun ready to be fired. I pull the trigger and drop the first bullet at exactly the same time. Which one hits the ground first? They'll hit the ground at the same time. How many people are going, no way, that's so not right, Coder. Okay, you shot one, it was moving. The other one you just dropped. They can't hit the ground at the same time. But they can. What do they have in common? Right, I didn't shoot the other bullet up. I shot it horizontally. So they both have to fall the same distance. Does gravity act on them equally? Yep. Okay. It doesn't matter whether you're moving or not. Gravity acts on you the same way. Okay. It pulls on you at 9.81 meters per second squared. Both of those bullets hit the ground at the same time. Not in the same place, but at the same time. Okay. Mythbusters actually did a thing where they proved that one day. So we have these projectiles, and that's how they work. Okay. Now, that means, though, that if I am trying to hit a target with a bullet shot from a rifle, I need to correct for the fact that the bullet's going to what? It's going to drop. As it flies, the bullet is going to drop. Okay, a short shot, I don't need to worry about it too much. Bullets go really fast. Okay, but longer shots, I do have to worry about it. Okay, in 1 second, bullet can drop 4.5 meters. In 1 second. Okay, so if an object is fairly far away from me, that's something I would need to consider. Okay, and I would have to aim well above my target. You see this a little bit more with a bow and arrow. If anyone's ever shot, like done archery, okay, because an arrow moves a lot slower than a bullet, you actually can see the arrow drop as it goes along its path. Okay, same with a rock or something like that. When you throw it, you can see it drop. Okay, bullet does the same thing. All right. So longest shot ever made by a sniper. Anyone know who holds it? It's a Canadian guy. Okay, Canadian sniper holds the longest kill shot, and that's kind of morbid, but okay, he holds the longest kill shot, nearly 4 kilometers. Okay, nearly 4 kilometers. He almost doubled the previous record with that shot. Now, imagine something is flying 4 kilometers. That shot takes several seconds. The bullet is in the air for several seconds. That means it falls a long way. Okay, and this is a shot taken in the real world across a canyon. where winds can affect the path of the bullet. Cold air pockets can slow it down, speed it up, cause it to do all kinds of weird things. Okay, yet this guy made that shot. Okay, it's something you really have to take into there's a lot of factors to take into account when making a shot like that. That's why so few people would ever be able to hit a shot like that except for blind luck. Okay. So longest kill shot, almost 4 kilometers. Okay, bullet in the air for a very long time. You almost have to correct for the fact that the earth is going to spin underneath the bullet as it flies. It's in the air that long. Okay, all kinds of things have to be accounted for. Now, here's the scary thing about that. If you're the target, will you hear the bullet? Nope. Okay, rifle bullets, especially high caliber ones, can travel several times the speed of sound. Okay? They actually have footage of like this stuff in Afghanistan where it's like the sniper cam kind of thing, but it's when the shots miss, the people that were the intended target do not look towards the gun. They look at the ground where the bullet hit, because that's what they hear. They see the puff of dust where the bullet hits, and they hear the sound of the bullet hitting the rocks. Then they go, because a few seconds later, the sound of the shot gets there. Okay, you imagine you're getting shot at and you don't even know it. Okay, it's that whole shock and awe strikes a lot of fear into people. Okay, when they think they might get shot and not even know it. Okay, that can be pretty scary. So there's that psychological aspect to that. If you've ever watched American Sniper, it's a good movie, but the book's better. Yeah, they talk about a lot of that stuff in that book. So, okay, with projectiles. Okay, a projectile is defined as any object in unpowered flight in the Earth's gravitational field. Okay, for our purposes, we're going to be doing this close to the Earth's surface where gravity is going to be 9.81. The higher up you go, the less that number becomes, and it changes things a bit. Okay, it usually has 2 dimensions to its motion, a horizontal dimension and a vertical dimension, unless you threw the object straight up in the air. Okay, then it would only have 1 dimension. Right? So in that way, it works a lot like the boat questions that we talked about before. Okay, it has a vertical and a horizontal dimension. Okay, the vertical dimension experiences accelerated motion, and that's because gravity is affecting it. The horizontal dimension moves at a constant speed. There are no forces speeding up or slowing down the projectile. Right? So it would just travel at a constant speed. Okay, so the idea here is that in the Earth's gravitational field, what goes up must come down. Okay, and gravity is going to pull the object towards the Earth while it moves horizontally. Okay, so that means that an object fired horizontally has the same flight time as an object that's dropped. Okay, we talked about that already. It also means an object projected at an angle into the air or vertically into the air will return to the original height at the same speed it left at. All right, so if I throw something up in the air and then I catch it at the same height I threw it from, it'll be going exactly the same speed I threw it at, just in the opposite direction. Okay, now that's in the perfect world, okay, where air resistance doesn't play a factor. Okay, if you shot a gun straight up in the air, you wouldn't have to worry about getting killed by the bullet when it came back down. All right, because in the real world, the bullet will travel, in its proper orientation upwards, but as it slows and starts to fall, it will tumble. Okay, and when it tumbles, it doesn't go nearly as fast. Okay, I'm not saying shoot a gun straight up in the air and then wait, but obviously the chances that the bullet would fall perfectly straight back down are astronomical. Okay, and because it would tumble, okay, it's not going to be moving at like a lethal speed. Okay, at that point, right? Everybody kind of follow me there? Don't play with guns. Okay, please don't. Okay, don't try any of these things at home. All right, but yeah, we're talking about perfect physical world here where air resistance is not a factor. Then yes, the object comes back down at the same speed it was projected at. Okay, and that's because obviously its rate of acceleration up and down, on the upward part of the flight and the downward part of the flight are both 9.81 down. Okay, and it's the same distance up and down. Right, so the velocities have to balance out when it comes back. Right. So what we have, okay, at least initially, is for an object that's projected horizontally. Okay, so if I like roll a ball off of a building. Okay, so if I just roll a ball off the top of a building. Okay, it's going to do this. Okay? If you've ever watched, like any Hollywood movies where a car drives off a cliff, like at first it's like all horizontal, right? This thing is like traveling outwards, and then it seems like it all becomes vertical really fast. Well, actually, that's true, because horizontally, its speed doesn't change, but vertically, it goes faster and faster and faster. So by the time it's getting, near the rocks at the bottom where it's going to explode, because for some reason cars always explode in movies, okay, it's going to be going much more vertically than it is horizontally at that point, because gravity will be accelerating it downwards. Okay. Now, if I project something, so I throw it at an angle, okay, then it's going to follow this path, which we call a projectile arc. Okay? All projectiles have an arc based on the initial angle and velocity at which they were thrown. Okay? The steeper this is, okay, the shorter that arc will be. Okay? The higher it'll be, but okay, the shorter horizontally it will be. Everyone all right with that? You probably realized that when you were a kid and played with the hose in the backyard, right? And your brother or sister was just too far away, so you just angled it a little bit more and then would go a little further. Okay? If you angled it too much, it'd start coming back to you. Okay? Come on, you all know you did. Okay. Again, that's just simple projectile stuff. Every droplet of water coming out of the hose is an individual projectile, and they're following the same rules here, okay, that we would follow. All right. Everyone okay with those ideas there? All right. So as we were saying here before, okay, if you're trying to hit a target, okay, with any type of projectile, whether you're throwing a rock or you're shooting a bow and arrow or you're shooting a gun, okay, you have to account for the fact that the bullet is going to be influenced by gravity and as a result is going to drop. Okay, if you've ever seen the movie Saving Private Ryan, okay, the scene where Vin Diesel gets shot. Incidentally, he's in that movie like for a short period of time, but okay, he gets shot by the sniper who's in a clock tower, okay, or a church tower, okay, quite a ways away. The sniper in his unit has to take him out, and he's talking about the shot that he has to make, and he says it's about 800 yards, maybe a shade under. That's 2 clicks. Obviously, he doesn't mean 2 kilometers because 800 yards is not 2 kilometers. Okay, but then he takes the scope of his rifle and clicks it twice. Okay, and what he does when he clicks it twice is he angles the scope downwards, so that in order to get the target in the crosshairs, he actually has to have the barrel aimed above the target. Okay, so all he's done is click the scope to account for drop. Okay, and so because his scope, this is supposed to be the rifle. I don't draw very well. I saved this one because it's the best one I ever did. So I just use it. Okay, so the scope is aimed downwards like this, which means to get the target in, the barrel has to be lifted up. So it essentially causes your shot to follow this arc and strike the target. Okay, otherwise, if he didn't do that, he'd hit the wall of the clock tower well below his intended target. Okay, and this is also another thing that Mythbusters busted, because in this scene, the American sniper shoots the other sniper through his scope. Like the bullet actually travels through the scope and gets him like in the eye, which is physically impossible, right? Because the bullet would have been traveling like this, and hitting all the stuff inside the scope would have like torn the bullet apart. So yeah, it was like really far-fetched that it wouldn't happen. Mythbusters did a thing where they shot a bunch of like busters through the scopes of other rifles and basically found it didn't work. Okay, all right. Everyone okay with that idea there? Okay, the fact that everything is going to drop, okay, as we go along. Right. Okay, so here's what we're going to do. We're going to have a look at a couple of projectile motion videos, just kind of get a feel for what this looks like. Some of them good, and some of them not so good. All right. Be recording. Okay, so if something goes off a cliff, it's going to move horizontally at a constant speed. Okay, but it's going to accelerate in its vertical dimension. So for any projectile motion problem, the first thing we want to do is separate those 2 parts, okay, because they don't have the same kind of motion. The only thing that they're going to have in common is what? Time. Okay, the only variable that the horizontal and the vertical parts of any projectile have in common is time. Because once it hits the ground, it's neither moving horizontally or vertically anymore. All right, so their time is always going to be the same. So from a vertical standpoint, if something goes horizontally off of a cliff, what's its initial vertical velocity? 0. right? It was moving horizontally. It didn't have an initial vertical velocity. So driving horizontally off a cliff and dropping something off a cliff from a vertical perspective are the same thing. Okay, initially they have no vertical velocity. Okay, we know that they're going to accelerate at 9.81 meters per second squared in a downward direction, and whatever the height of the cliff is would be the displacement of the object. All right, what's the final velocity going to be? Well, I only ask that because that's what often people will say is it's zero. It's zero after they hit the ground. We talk about the instant they hit. How fast is it going then? The answer is it depends. It depends on what? Well, time, and time depends on how tall the cliff is, right? The taller the cliff, the faster the object will be moving when it hits the bottom. Okay, does that make sense to everybody? All right, so we don't know what VF is. We can calculate it if we have enough information. Okay, from a horizontal standpoint, okay, so what I usually do when I'm doing a question like this, okay, is I just put the horizontal information over there. I put the vertical information over here. I keep them separate. Okay, from a horizontal perspective, okay, all I have is how fast was it going when it drove off the cliff. So maybe we could say it was moving at 25 meters per second. Well, okay, that number's not going to change. It's not VI, it's not VF. There's nothing that's going to speed it up or slow it down horizontally. And that's the part that sometimes people have trouble with because they see this object and see that it's definitely going faster as it falls. And I'm not denying that its speed changes as it falls, but its horizontal velocity doesn't. Okay, its vertical velocity does, its resultant speed does, but its horizontal velocity does not. Okay, it's going to move at the same horizontal velocity the entire time. Okay, everybody all right with that idea? Okay. So let's maybe look at a problem that's kind of like that and see what kind of things we might encounter for a problem like that. So let's just do this one as an example. That's ground, not groard, ground. Okay, so I've got this ball, I'm throwing it horizontally at 18 meters per second off the top of a 30-meter high cliff. Okay, that would include like whatever height I am as well. Okay, that 30 meters is included in my height for throwing. Okay. And I throw it at 18 meters per second, straight horizontally outwards. I want to figure out how tall is the cliff. So if I'm drawing a diagram here, it's going to kind of look like this. And I'm going to say, all right, here's my vertical information. Here's my horizontal information. Okay, horizontally, I know how fast it's going. It's moving at 18 meters per second, and that number's not going to change. Okay, if that number's not going to change, then from a horizontal perspective, the only formula I can use is that one. Problem is that I'm looking for the horizontal distance. I'm looking for D. What do I need in order to get that? Time, which I also don't have, at least not yet. All right, vertically speaking, how fast is the object going initially? 0. I threw it horizontally. All right, how far is it going to fall? 30 meters. What's its acceleration? 9.81 meters per second squared. All right, now I could put negatives on these, but it's really not necessary because the object's not going to change direction. It's all going to be downwards. Everyone okay with that? Okay. So I need time. Okay, I need to find out how long this thing is falling for so I can figure out how far it goes horizontally. Can I find that with these three pieces of information? Okay, because just a minute ago we said time is the only thing that the vertical and horizontal components share. So if I can find it with one, I can use it for the other. And right now I have VI, A, and D. And I'm looking for T. Do I have a formula that has those four things in it? Yeah, this one. You know, remember that one I told you I'd never ask you to find time with? Except when VI equals 0, which it does. Okay, so I can solve for time. Right? And that's what I'm going to do. I'm going to manipulate this for time. So I'm going to divide both sides by half of A, and then I'm going to square root. Okay, that'll leave me with T. Okay, so we got 30 meters divided by 1/2 times 9.81. Whoop, missed the 8. Okay, so it's going to take 2.47 seconds for this ball to reach the ground after I throw it. Okay. So that entire time that it's falling is also the time that it's moving horizontally. And it'll continue to move horizontally until it hits the ground. Can I find D, the horizontal D now? Yeah, now I just use D equals V times T. Right? Take my 18 meters per second, multiply it by the time there. Okay, using all my digits. All right, so it's going to travel 44.5. Actually, we only have two significant figures, I think. So 45 meters horizontally. All right, so it'll be 45 meters from the base of the cliff when it hits the ground. Okay, so it's a new context, right? We've never had a problem that's worked like this. But have we done every part of it? Yes. That's what you have to remember about projectile motion. The context of these questions is new, but the method to solve them is not. Every single part of these we have done. Okay, that was V equals D over T and accelerated motion, and that's it. Okay, now the ones projected at an angle, they're going to bring in some vector stuff. Okay, all right. Everybody all right with how that one worked? Okay. Now, in the modern Hollywood, the one you guys have experience with, reality is constantly suspended. Not that it wasn't suspended when I was a kid, but okay, they couldn't pull off the same stuff when I was a kid that they can now because they have CG. And they can make anything look real with CG. Okay, which means they can break all the laws of physics they want and still make it look cool and look real enough. Okay, when I was a kid, if they wanted to jump a bus over a gap in a road, they actually had to jump a bus over a gap in a road. Okay, they could film it from different angles, cut it, whatever, but in the end, they still had to destroy at least one bus. Okay, probably 2 or 3 in order to pull off the whole shot. Now they just take a film of a bus driving up towards the edge, and then they just get a computer to do the rest. Okay, and it just looks ridiculous. All right, so movie physics is not good physics most of the time. I'm going to show you some examples of absolutely horrible movie physics. And I mean like beyond horrible. Okay. So, how many people have seen the movie Speed? Keanu Reeves, like pre-Matrix Keanu Reeves, like a really young man in this movie. Okay. No, this is the bus that jumps over the gap in the freeway. It's the worst. It's one of the worst examples of like violating the laws of physics in a movie ever. And it's also an example of terrible editing. Terrible. Okay. All right. Okay. We want to look at what happens when something is projected, okay, at an angle. All right, so we're going to watch here first it was a YouTube video that went totally viral many years ago now, but okay, and it was of this guy who created what he called the mega whoosh, which was this giant like slip and slide, but he put it on a big hill, right? And then he built this ramp, and he went down the hill on the slip and slide, okay, and then shot himself off the ramp and landed in this tiny little kiddie pool. Okay. Yeah, like people were like, holy crap, that's the most amazing thing ever. How did he do that? Okay, so we'll watch that. Okay, we'll watch the initial video, and then we'll kind of think about maybe how that works, and then we'll look at how the Mythbusters, what they did with it. Okay, so this is the setup for that. Okay, he's essentially got this big ramp, and he's going to shoot himself off the end of it. Okay, and he's going to travel in this projectile arc that encounters the ground over there. Now, here's what we're going to assume. We're going to assume that the takeoff point here and the kiddie pool are the same height, right? Because it kind of looked that way, right? Like the kiddie pool was kind of up on the hill, so it was about the same height. We're going to say it's the same height as the end of the ramp. Okay, so he's going to fly off the ramp following this with this here, 20 meters per second. We're going to say, right? Now he's moving at 20 meters per second, 30 degrees above the horizontal. He follows this projectile arc. Now, along in this triangle here, this is where the vector part comes in. Okay, what I want to do is I want to break this question up into vertical and horizontal parts. That 20 meters per second is angled. It has a vertical component that will be our initial vertical velocity. Initial because it's going to change due to gravity. And it's got a horizontal component that will be our constant horizontal velocity throughout the entire flight. Can I find those two sides of the triangle right now? Yes, this is just finding vector components, right? Finding x and y. We're good at that. All right, so for VI, that's going to be the sine of 30 degrees times 20 meters per second. So VI is going to be 10 meters per second, and I'm going to make it positive because it'll be upwards. He's initially moving upwards when he comes off the ramp. Okay. Horizontally speaking, we're looking for the adjacent side. Okay, so V horizontal will be the cos of 30 degrees, okay, times 20 meters per second. Not 330. Okay, so horizontally, every second he's going to go 17.3 meters. Again, remember he hit that tiny little kiddie pool. Okay, you can't run this fast, 17.3 meters per second. Okay. All right, and that number is not going to change. All right, what goes up must come down. How fast is he moving vertically when he comes back down to the pool? 10 meters per second. Okay, because he's going to move upwards. Okay, so essentially if I'm just watching this from a vertical perspective, like I'm straight behind him, all I see is that he goes up and then he comes back down, exactly the same distance and exactly the same amount of time at exactly the same rate of acceleration up and down. That means that when he comes back to the ground, or the kiddie pool, he's moving at the same speed vertically that he left the jump at. Everyone okay with that? All right, so his VF is negative 10 meters per second. I want you to imagine hitting a tiny kiddie pool at 10 meters per second. Okay, that's really fast. It would hurt a lot. Okay? It would be like running into a wall. Like you're running basically as fast as you can. Don't get your hands up, run into the wall. Okay, that's what that's going to feel like. Right? Okay, so negative 10 meters per second. And the other thing I know is that gravity is involved. So I know VI, I know VF, and I know A. Everyone all right with that? All right, so if I know this information and I'm this guy, can I figure out where to put the kiddie pool? Yeah, okay. I can easily figure out where I should place this kiddie pool in order to save my life. All I have to do is figure out how far I'm going to travel horizontally. Okay, I need to figure out what is going to be my horizontal displacement. I only need one number to do that. What is it? Time, right? I need to know how long I'm in the air for. Can I find that with these three numbers? Yep. I go back and I use my good old Science 10 acceleration formula and I solve for t. All right, so I'm going to have T equals VF minus VI over A. So that's going to be negative 10 minus 10 over negative 9.81. So we're going to have negative 20 divided by negative 9.81. Okay, this guy's in the air for 2.04 seconds. All right, he's moving at 17.3 meters per second for 2.04 seconds. I can figure out where that kiddie pool's got to be. Okay, I just have to multiply those two numbers together. Okay, and I've got my total displacement, V times T. All right, 35 meters approximately. Okay, so I'd have to put this thing 35 meters away. I mean, if I was this guy, I'd want all those decimals. I wouldn't be rounding anything off. Okay, but yeah, okay, about 35 meters away, and I should be good. Right, that's a long way, 35 meters. Right, that's like 100 feet. It's a long, long way. Hey, Mrs. O. Okay, so does everyone kind of follow what we did here? All right, it's basically just, again, there's nothing in this that we haven't done already before. Okay, we've found vector components. We've done acceleration problems in V equals d over t. Question? Okay, so from a vertical perspective, even though this thing's moving at an angle, if I can only see the vertical part, I see something start moving upwards at 10 meters per second. As it moves upwards, it slows down, right? Because gravity's pulling it down. So it reaches a maximum height where its velocity will be 0. So now it's going to fall back down exactly the same distance at exactly the same rate of acceleration, which means it has to get back to the speed it left at. It is. That's what's causing that to happen. It accelerates due to gravity on the way up, but it's accelerating down. That's why it slows down, right? So if I've got, essentially what we see from a vertical perspective is the object moves upwards. Here, VI was 10 meters per second up. And up here, VF was 0. Well, now it's going to do exactly the opposite thing, okay? VI is now going to be 0, and VI is going to be negative 10, because what they share is that it accelerated at 9.81 up and down. Yeah? So everything is the same, so it has to get back to the same velocity it left. Does that make a little more sense? Okay. Okay. Any other questions on how that one worked? All right. So looking at that and just thinking kind of logically, because when you first watch that video, it's like, oh, wow, okay, I want to try that for you crazy people. Okay. But it's pretty impractical to think that something like that would actually work. I don't know how many lawsuits these guys probably faced afterwards from people nearly killing themselves, okay, trying to repeat this thing. Okay, but the Mythbusters did, okay, and I'm going to show you those videos tomorrow after your quiz. Okay, so I will post your quiz tomorrow, okay, and then we'll go over some more projectile motion stuff. Okay, so you got a few more minutes left here, guys. You can work on either your map activity with your group or your vector assignment, okay, something like that for the last few minutes here.